how many questions are there anyway in the homework? There's 14, so they're all about x's or y-axes. Let's do a straightforward one, then an awkward one, and see how things go. So this is question 13. And the curve is -3y squared plus 15y take away 18. And it's x equals 0. And the whole thing is going to be rotated about the x-axis. Right. So I'm going to be putting this into Desmos in a minute, but what I'm kind of going to look at is here. This says it's going to be about the x-axis. That means any formula that are mentioned, in this case there's just one, any formula that are mentioned should be in the form x equals a function of y. So I know this one is good to go. I don't need to algebraically change it at all. So what I'm going to do now is I'm going to do a little sketch of it so I can get an idea of what this thing is going to look like. Because we need to know start and finish values. At least, you know, what we call the C and the D. Now let's see what we've got here. Just getting, hey, where's Desmos gone? I had Desmos. Okay, I'm going to get Desmos again then. I thought I'd set up Desmos, but evidently I closed the window that I didn't know I'd closed. Okay, we should be good now. So I'm going to go into Desmos, type this guy in, see what he looks like. It's definitely a quadratic, so it'll be some kind of C-looking shape or backward C shape, more likely. Here's Desmos. If you type in x equals -3 y squared plus a 15y take away 18. Yep, backward C. The other one is x equals 0, but we should all realize that's just the y-axis. And bring this along and kind of zoom it in a little bit. And we're basically talking about this shape here. You agreed? The shape here? Right, so I'm drawing a little picture of it. Desmos is telling me it's 2 and 3, so that's easy to figure out. Right now I'm just doing a little quick sketch of the thing. Right. So my first step in this process is use Desmos or draw it by hand if it's easy to do. Draw a picture of what's going on. And we can then move on to the second phase. So that's essentially what the picture looked like. And the second phase is, which situation we're dealing with? Well, degree, it's definitely one curve. And it's an x-axis. And a one curve x-axis is this guy. So we know the formula. It's integral from C to D, 2 pi y, f of y dy. So it's going to be from 2 to 3. Oops, put my 2 pi outside. That leaves me with a y and this ugly expression. Sometimes you have to do some, you know, algebra on it. Nothing horrendous. Just distribute the y. And at that point, I think the question's pretty much over with, isn't it? Do a power rule and plug in 2 and 3 and remember it multiply by 2 pi at the end and you're good to go. Okay, so let's show you an awkward version of that. Question 12. It's an example of that. I think this probably explains, well, to me anyway, explains why it's important to draw sketches to see what on earth is going on here. Definitely going to be rotating this curve, and that's a boundary line. This is another boundary line. So I'm going to try and draw a sketch of it. This time, I'm just going to do it on my own and tell you what the result is. That way it saves me, nipping back and forward all the time. So I'm just typing it in the way it's actually written. Hopefully. I need those brackets there. Okay. Believe I have got it right. And it looks like this fella. Okay. And it's going to be rotated about the x-axis. And if I type in y equals 8, can we assume that it's here? And if I type in x equals 0, we'll assume it's here. And that means that you put this package together. I've lost my red pen. It's this little piece in here that's going to get rotated. We comfortable with just imagining that I did it in Desmos and you got that? That line is the y equals 8, and this is x equals 0. So you've got this little axe head shape rotated about the x-axis. It looked like an ashtray for those people who still have ashtrays in the house. So what we're going to do now is realize that there's something wrong with the information in the way it's given. And that's the guy that's causing the trouble. I am going to be using this formula here, right? Rotating about the x-axis, single curve, right? But that needs to be written as x equals a function of y. So let's see how we can rewrite it so that it's in the form that we can use. Lots of ways of doing it. I don't care how you do it, but I do need you to do, well, to tell me what to do. So I'll take volunteers. I want x equals on its own when I'm finished.
X to the 3/2 would be the same as x, the square root of x cubed, right?
Okay. And you're
So we
right.
could take the square of both sides and then the cube root.
Squares of both sides. And then the cube root, which I'll just write as a fractional power. Yes, that works well. Are you happy about if y equals x to the 3/2, then x is y to the 2/3? Do you notice that there's a shortcut? And what you said is perfectly fine, and I like it. Can anybody see the shortcut where you can go from the start to the end right away?
Use the reciprocal.
Yeah, it's a reciprocal. Do you notice the 3/2 becomes 2/3? So y equals x to 7/5 would become x equals y to the 5/7, that kind of thing. Right, well, it's all ready now. We've got everything we need. 0 to 8. 2 pi y, this fella. Pull out the 2 pi, at least I like to do that. This guy times this guy. What do you think I'm going to do about y times y to the 2/3?
That'd be y to the 5/3.
Just combine them. Would you agree that this is now just a ugly version of the power rule? Right, add 1 to the power, divide by the new power, and off you go. And that is the end of that question. Any questions so far? We go. Right, let's see who's left. Don't know. Let's see. I'm not 100% sure if this is going to be anything particularly clever. It may actually be a very boring curve, but I think it might have some little kick in the tail here. Because I'm trying to visualize it and see what I got. So here's my little sketch. Here's the axis that we're going to rotate it about. Ah, interesting. See something coming already. There's the square root of x. Here is x equals 0, and here is y equals 5. That is a cool question. Right, so it's an axe head. Is there anything that we need here? Because since it's going to be rotated about an x-axis, right?
We need to write the information in terms of height.
So what would this be rewritten as then?
Equals y squared.
Okay, so I can't quite hear what you're saying, but we have
Sorry,
this.
x equals y squared.
Agreed. We agree that that's it. Do we have a 0 to 5 thing going on? Yeah, would you agree? Everything else is pretty much it. So I'm not going to complete that one. It was just a rearrange that guy. I thought something a little bit more interesting was going to happen, but I was wrong. Keep trying to find something more interesting. Okay, I think we've done this one. Maybe not. Right, for the last one then. I've got a feeling I've done either this question or something really close to it. And this is going to be about the y-axis. Okay. Well, I might as well complete it. If we haven't done this one, that's great. If we have, they keep changing the numbers anyway, so it will always be a little bit different. Right, this one is about a y-axis. 6x minus x squared looks something like this. Imagine I already had it in Desmos. Y equals x is something like that. And this guy here is 5. And so when you put that whole package together, that's the shape that's going to get rotated about the y-axis. Okay, so would you agree it's 2 curves, y-axis? So what we're looking at here is this fella. So it's going to be the integral from a to b 2 pi x. I'll call it f of x, take away g of x, dx. So it's going to be from 0 to 5. Stick out the 2 pi. and x. One of these two guys is f of x. The 6x take away x squared 1, or the y equals x1. Who goes first?
Is it y equals x?
Well, let's have a look at it. One guy, two guy. If I draw one of those funny little vertical rectangles, who's tallest? Who's further up?
6x minus x squared.
You agree? The curve? Now, from time to time, we get them back to front. If I did do it the other way, wouldn't the answer be just negative 12 pi instead of the right answer, which would have been plus 12 pi? So we would know when the answer came out that it is negative. So when you are rotating about the y-axis, the higher function is f and the lower function is y. When you are rotating about the x-axis, the one furthest to right will be the f, and the one that's not, I guess the one to the left of that will be the y. So f and g, f and g. It's the easiest way for me to remember. Right, this fella here doesn't need too much, but I'll do a little bit more. If you subtract these two and then multiply by x, you get that guy. And that guy is a power rule, isn't it? And you're finished. And hopefully I've covered enough combinations that you've seen to be able to do those questions in homework. Anything to talk about before we move on? Anything that you want me to go over? Okay,
Can we look at number 5 on the homework?
sure. Let's see what's going on in question 5. And, well, I'll just write it down because it's quicker. Right, in question 5, we have got a really ugly function, which is that guy. And then we have a whole load of y equals zeros, x equals zeros, and x equals 1. And the thing is going to be rotated about the y-axis. So I'll start with my picture of it, and I'll do red because I can. That's basically what 3e to the negative x squared would look like. Now, if you plug in y equals 0 and x equals 0, right, x equals 0 gets you the y-axis, and y equals 0 gets you the x-axis, and x equals 1 gives you the guy that's there. So when you put that line, and this line, when you put the whole package together, all that information tells us is this is the area that's going to be rotated about the y-axis. So I can set that part up. So it is going to be a single curve. So it's going to be the integral from a to b, 2 pi x, f of x, dx. It's going to be from 0 to 1, 2 pi x times 3e to the negative x squared, which is what f of x is, dx. What I would do now is pull out the 6 pi and leave behind that ugly guy. What technique am I going to use to integrate this ugly guy?
U sub
And who will the u sub be?
negative x squared. Actually, would it be negative x squared or just the x squared?
The good news is both work, so it doesn't matter.
Right.
Is that enough to just say dot, dot, dot?
Yeah.
Okay. It's going to be ugly, but quite a lot of these answers are ugly. Always be aware, this is a physical volume. All these questions exist in the real 3D world, which means that they must be positive numbers. So if you ever get a negative answer, it could simply be that you got your F and G mixed up. And so if you get -5/2 pi, try 5/2 pi, because there's a good chance that you did everything else correctly. You just switch the two. And that's an easy fix. Even in a test, it's easy, because all you will write down is a quick sentence saying, switch the positions of F and G and give me the answer as a positive value, and you should be fine. Okay, so that was a good question. I like that because I didn't realize there was one of those ugly substitution methods floating around, because a lot of the questions just seemed to be power rules, didn't they? But that one wasn't. Any more questions before we move on? Okay, no questions is good. We have covered everything you need to do for the homework, but we have a big section to do, and I want to get started, and I probably won't get it finished. In fact, my guessing is that I won't get it finished on Friday either, because there's a lot in this next section. And I am going to become a physics teacher, which is scary for me and will be quite hilarious for you lot, because I am not a physics person or engineer person for that matter. And so I am going to try my best to show you how integration can be used in the world of science. And in particular, we're going to look at a topic called work. We are going to calculate work. So this is going to be chapter 6.5. Its heading is work. And we are going to look at calculating work. With no calculus at all. Calculating work with calculus. We're going to do spring questions, which is actually a biggie. I believe it's called Hooke's Law. Does anybody here know what Hooke's Law is? To do with springs and forces acting on springs and the work done in stretching and compressing springs. No one heard of Hooke's Law? Okay.
I used it in my old physics class. It's been a while.
Okay, so it's something that's rusty. You've seen it a little bit, but nothing too major, right? Okay, try to think of what you call the next one. I can't think of a good one, so I'm going to give you a bad description of it. Pulling ropes up cliffs. Doesn't make sense, but it will. And that's basically, yeah, that's basically the types of questions that we're going to deal with. So we're going to calculate the work done in moving an object from where it is to where it ends up. So let's give you a very simple example of calculating work when there's no calculus involved. So suppose I had a mass, and this is in metric, of say 120 kilograms, and I raise it from a height 2 meters to 3.5 meters. Gravity is going to be 9.8 meters per second squared. Okay, there's a magic number, 9.8 meters per second squared. Do you recognize that number from any science class that you've seen?
Is that gravity?
It's
That
the
is gravity.
acceleration of gravity.
Yes, acceleration due to gravity is gravitational constant, at least on Earth. On the moon, that number's a lot smaller, for instance. Now, this is a question that you could have gotten, I guess, is it physics? I'm trying to think of what branch of science does work. Anybody?
Yeah, that's physics.
It's physics, right? So in physics, you may get a very straightforward question, such as the one I've just described, right? Do you see what I mean? That I feel like I'm a science teacher right now, and that's not my strong point. So if I feel a bit hesitant, it's because I don't want to tell you something that's wrong. The calculations I like. Okay, so the basic formula for getting work done is force times distance moved. In this world, the force is basically caused by 120 kilograms multiplied by the gravitational constant multiplied by the distance moved. So this number here, basically the mass. So it's going to be 120 times a fixed number, 9.8 in this case. And the distance from here to here is what, 1.5 meters. And then you put the whole thing together and you get 120 times 9.8 times 1.5. And the answer I get is 1764. And the units are joules. Is the units also called Newton meters? I don't want to write it down if I'm wrong, but somebody said, yeah, you can call it Newton meters if you want.
So is what we're calculating joules, is that the potential energy it has, or is that if it falls
That
all
is
the
the
way to
work,
the ground?
that is how much work was done in moving this rock. So imagine
Oh,
the
okay.
ground and you've got this rock and it's 120 kilograms. And right now it was 2 meters off the ground, but I moved it up to here. And that new height I moved it up to was 3.5 meters. And the work that is required to pick this thing and hump it up to here ends up being that number of joules. Now, if you wanted to know things like its potential energy, you would have to, I guess, assume how much energy would it give if we dropped it and it hit the ground. Well, that would be its mass, which is 120, times gravity, which is 9.8, times 3.5. And I guess that would be the potential energy. We've essentially added some potential energy to this rock because right now it's already got 2 meters worth of potential energy, right? It's already above the ground. So if I let it go, it would give you some energy right away. For those who can understand what I've just said, is that reasonably consistent with what you've been taught? I don't want to go someplace where I'm saying something backwards. We feel good? Right. So this is an American anomaly, but unfortunately, you also use feet and pounds. Nobody knows why, but you still use it. So if you have a question involving pounds and things being raised or dropped from feet, for instance, you might get a story like this. A 1,200-pound piano is lifted from the ground to the third floor, which is 30 feet away. How much work is done in doing that? Well, it's force times distance. And the force in this case is just 120 pounds. And the distance is 30 feet. And so the work done in moving that piano from the ground up 30 feet is 36,000. And the units you use here are foot-pounds. So metric and imperial. What's the difference? This guy has gravity in it. This guy doesn't need it, because when you say something weighs 1,200 pounds, I guess you're already including the fact that gravity is included in that number, essentially. Because see, if you took a 1,200 pound piano and you moved it to the moon and you put it on a set of scales, would it still weigh 1,200 pounds? Nope, because the gravity on the moon is different, evidently. You don't care when you use foot-pounds, because I guess you're just going to pretend that pianos never leave the earth, which is probably a pretty decent assumption. So that was examples of calculating work with no calculus. You plug and chug, don't you? Somebody gives you a formula and they tell you, this is the formula, these are the numbers, put them into the formula and grab a calculator, right? So let's look at calculating work done, but this time using calculus. So we're going to use basically a thing called the force function. Now, what this allows us to do is to model things a little bit more realistically. When we did the first two questions, the rock weighed 120 pounds all the time. It never changed its value, right? From the beginning to the end of the journey. The piano weighed 1,200 pounds, never changed. Can you imagine you may get a situation where as the thing is moved from position, say the ground, upwards, it gets lighter? The one that comes to my mind is a rocket. Now, rockets have fuel in them. So when that rocket is fully fueled and it's on the bottom, it weighs a lot more. But as it travels vertically upwards, doesn't it burn up fuel? And so the rocket gets lighter. And therefore, the force that you would use, which is basically the oomph that you're going to get it to take it off into space, and won't that change through time? Because you've got the same amount of force acting on something that is weighs less, right? And therefore, actually, the net effect is that the thing accelerates as well. Right. So we do work with functions, or we work with forces that change through time. So a very common variable to use for a force function is capital F of X. And I want you to imagine that I give you a force function that says this. Now, this is a little bit weird orientation, but it's okay. I'm not calling X the X-axis. X is just vertical distance, right? You can just think of it like that. And so you can imagine that this force changes as things move up, upwards. Now, if you have a force function and I ask you for the work done in moving this object from X equals any number you like, say 1, to some other number, let's say 10. How would you do that? Well, the formula for calculating the work done is the integral from A to B of the force function. So just tell me what the force function is. Tell me where you start. Tell me what you finish. That's A and B. And I'll tell you how much work is done in that journey. So in this case, it's from 1 to 10. 3x to -2. this guy is actually quite nice because isn't this guy ready to use the power roll on? So I don't need to do algebra. So I'll add 1 to the power, and then I'll divide by the new power, and I evaluate it from 1 to 10. And now I'm going to break one of my rules. Technically, style points, is it not the correct form of the answer? Right? It looked negative, it's still negative. But why am I changing it into 3 over x? What practical advantage is doing this and writing it like that? Can you see any advantage in writing negative 3x to the minus 1 as negative 3 over x?
Is it just because it'll give you a clearer answer?
Yeah.
You're just dealing with fractions.
That's all it is. Sometimes the obvious answer is the right one. So what do I get? I get negative 3/10 plus 3, which is 30. So I get 20. Whoops, put it in the wrong place. I get 27/10 is my answer. Now, if I had left it like this, wouldn't I be doing 3 times 10 to the power of negative 1, take away 3 times 1 to the power of negative 1? Would you agree that that's kind of clunky? What is 3 times 10 to the negative 1? Can you imagine, you might just go to your calculator and go decimal on me, which we try and avoid, right? So it's just to make life easy. That's the only reason I did it. Now that does mean then that provided you can tell me what the force is at any given position x, right? So as long as you can tell me what the force is at any position x, and you tell me the starting position of x and the finished position of x, I can tell you the work done in moving this object from here to here, acted upon by this function here. So let's do a pretend story. Here is a weird planet. And on this weird planet, gravity changes the further away from the surface you get. That seem reasonable? Right. And it changes according to this formula. Gravity is 10 over x. And let's make it x plus 1. So when you're on the ground, won't gravity be 10? Right. And when you're, 10 meters off the ground, actually make it 9. When you're 9 meters off the ground, won't gravity now be 1? And when you're 99 meters off the ground, won't gravity be 0.1? In fact, tweak the numbers a little bit. Isn't that actually what happens when anything tries to leave the surface of the Earth? Is gravity on the ground the same number as gravity when you're 1,000 miles off the surface of the Earth? And the answer is no, it's not the same. Not true. I mean, if you were 1 billion miles away from the Earth, wouldn't the gravity, if there was no other planets in the universe, just Earth, right? Wouldn't the gravity be almost negligible? You wouldn't even know it was there.
I thought how it worked was you'd go higher up and gravity would reduce by very small amounts, just enough to like mess clocks up.
Oh yeah,
And
you have to go really far.
right. And then once you exit it and you get into orbit, there's no gravity.
There is still some gravity even in
there's
orbit.
still enough, like that's why you're in orbit and not.
Yes.
floating
And if you
around
go
in space, but-
further away, the gravity becomes so negligible that you won't orbit anymore. You'll just drift away somewhere. So, would you agree that this is a much more realistic version of what gravity should be like, rather than saying it's 9.8?
Yeah.
So this is a planet, right? And it's got a gravity potential that's quite strong. In other words, the gravity dissipates very quickly, right? So suppose I had an object at position 0, it's on the ground, and it's going to travel, say 100 meters into the air. Then what would the work done to make that happen? Well, it would be the integral from 0 to 100 of the force function dx. Well, isn't gravity, as long as it's 1 unit of mass, isn't gravity the force function? Now, what about if it's 20 kilograms? Well, don't you just multiply it by 20 and you've got that, right? So all you need to do is integrate your force function. So do you see, I can now do calculations where gravity changes through position. I can find the work done if I'm in a weird place where as you go higher, the gravity gets stronger. I have no idea what planet that would be, but we could do it as a calculation at least. That's kind of impressive that we can now do situations that you couldn't do in classic physics. Because in classical physics, you just get, you know, distance times force, right? Two numbers that get multiplied together, and that's the end of it. Are we good? To finish with, here is an object being moved along some direction x, and it's in meters. And here is the force being used to move that object. And it looks something like this. And it goes to 0, 2, 4, 6. And it goes 8, 10, 12, all the way to 16. This guy is a height of 18. And we are being asked to use this diagram to calculate the work done. Now, if you have a force position curve, which is what this is, right? It's a bit like a distance velocity curve, right? You do those. If you do a force and position curve, geometrically, what is the work done?
The area.
The area.
Yeah. Now, I don't need calculus to get this area. Would you agree? It's probably a lot easier just to do, you know, a triangle plus a rectangle. So what's that? 6 times 18. So the triangle is a half of 6 times 18. And then 10 times 18. And there's a mistake in this, but I know I've made the mistake, so that's good. That's 54, and that's 180. So that's 234, I hope. What is the mistake that I have done? Because if this had been feet and pounds, right, I would be fine. The answer would be 234 foot-pounds. But this is the meters and the thingies. So if gravity is involved, what should I do? Multiply by 9.8. And if gravity has already been included in the force, then I don't need to. So let me read the question. Don't know. There are two possible answers. It's either that guy, or you will have to multiply by 9.8 to get that guy. So when you do question 4, you can tell me which one it is. If the units are feet and pounds, you don't need gravity, it's included. If the units are in newtons, not newtons, if the, yeah, are newtons and meters, you better make sure, do you need to use gravity's constant or not? I'm not convinced I know what's happening in 4 the more I think about it. But I do know it's the area, right? That part I'm happy with. Is it just 234 or do you need to include the gravity constant? I think, yeah, perfect timing. So